Everyone, welcome. This is November 12th, 2025. Thanks for coming to our webinar. Today we're talking with Andrew Vaillencourt. Andrew has written 2 books and they sell a lot more than mine. His newest book, is it right? So 10 times more than mine this month, which is pretty good. But that's because his is on a topic people care about. In fact, you do, and that's why you're here. It's about energy efficiency. And his book's good, actually, really good. But that aside, you can look him up on Amazon, see what he's written. I think if you like what he teaches, check it out. But anyway, today we're talking about Waterside systems. And before I do that, I'll talk a little bit about Andrew. I don't know how I met you, Andrew. I think I saw you speak maybe at AE World. Is that how I met you?
Yeah. Yep.
Or it could be I was reading what I think I was reading what you're writing on LinkedIn. Might have been that too. But anyway, he's super impressive. I think he's a great writer. But what makes him really, I think, special is that he speaks to our level. It's something I also do. I don't speak over people's heads, or I try not to, and he certainly does not do it. But he's a great communicator, but he also has done a ton of energy audits, and so he actually knows what he's talking about. And with that, I'm going to stop introducing him. And if you have anything else to add, do it yourself, and I'm going to shut up. And why don't you take it away, Andrew?
All right, thanks, John. Yeah, hi, everyone. I am Andrew Vaillencourt. I am technically a certified energy auditor through the Association of Energy Engineers. I'm a second-generation energy auditor, like my father before me. About 21, going on my 22nd year in the business. And to John's point, yeah, about 1 billion square feet of audits and about $1 billion in projects. So I have seen a lot of stuff. I came up the hard way, came up through the old man, slapping me around and making me do all the grunt work in the field. And that's sort of my story. Yes, the 2 books. First book is Silver Bullets and Other Energy Efficiency Myths and Magic, and that one focuses on how bad projects get sold, how we miss savings, that sort of thing. And the recent one is simply called The Energy Efficient Facility, and that's sort of a building operators and energy managers guide to getting the most out of an existing building in the modern economic, social, and technological climate. So check them out if you want to. If you're having trouble falling asleep, they're both excellent at getting you there. That being said, today we are going to talk about waterside systems. And waterside systems, I love it because it's such a broad term. In the next 45 to 50 minutes, I'm going to attempt to cover what is an entire semester of mechanical engineering school. So don't feel bad if some of this hits and some of this doesn't. This is a 101 course. This is an entry level little discussion. So the good news is there will be no calculus. There will be no thermodynamics, no Fourier. It might be a touch of algebra, but I won't actually make you do it. I'm just going to talk about it. So that is for today. I see we have about 100 people on the call. Glad to see you all. Normally on these, I encourage questions. If you have a question, I don't know what the protocol is through this particular app is, but you can absolutely hit me with it. If I have time or if it makes sense, I can absolutely go into it. If I don't get to your question, don't feel bad. Hit me after, find me. I love answering questions. I love talking shop. I think that's about it. And I'll get started if everybody's happy. I need to do a show of hands. And we're going to get started. Our November webinar is Basic HVAC Waterside Systems. If you can't see my screen, holler.
We see it. There we go.
All right, very good. There are the presenters. Yep, there's John on the right. There is me trying to look like an extra from Miami Vice. A note from me. This presentation has been excerpted from a much larger course. There's a lot to discuss on such a broad topic. Some of the design and mathematical intricacies are really interesting and fun, and if you ask me to, I will go into them and use up all the time talking minutia. There's simply not enough time to go through everything with a waterside system. However, I have selected basically what I think is the crucial stuff, the meat and potatoes of it, and limited the slides to hot water and chilled water systems for the most part, simply because that's all we're going to have time for. For a lot of you on the call, there's plenty of us here. This material may be remedial. I apologize if it's a little underneath you. Some of this material may be new to you, which is awesome. That's what we're going for. We want to expand your understanding of these systems. Please take what is helpful for yourself and discard the rest. I do not mind. I will not be offended. All right. Principles, applications, and innovations. Why did we pick water? This is 101. So we're going to talk about why we even use water in the first place. In the old days, we'd use steam to heat. for lots of reasons. Don't have to pump steam. Steam moves all by itself. Steam is easy to make. Lots of great reasons to use steam. But water is safe. You can drink it and even breathe some of it. As a matter of fact, it's so safe that not drinking it will kill you. Absolutely nobody gets excited over a water leak unless it's over a carpet or drywall. It doesn't pollute. Water leaks are not big environmental catastrophes. There's not a lot of regulation on it. Although there's plenty of regulation on water these days, but compared to ammonia, water is pretty tame. You don't need special safety protocols or equipment to work with it. You need galoshes, all right? You don't need a fancy moon suit or anything. And number two, it moves easily. As easily as steam? No, but it moves easily. It has a specific gravity of 1. It is the basis for which we do our specific gravity calculations. And it flows nicely through small pipes. It is a low friction, low Reynolds number fluid. So it flows nicely through small pipes. It's inexpensive, relatively, I suppose. We live in a world now where water is its own special thing, but it is significantly less expensive than all of the alternatives. And if your system is a closed loop, and I hope we all know what I mean by closed loop, and that it doesn't send the water to the drain, and your system certainly shouldn't be sending water to the drain, you only have to buy it once. So if I have 9,000 gallons of water in my chilled water system, I will only ever need that 9,000 if it's a perfect system. We don't live in perfect systems, but generally speaking, you buy the water once and it's yours. You own it forever. Enjoy it. It has excellent heat transfer properties. It has a specific heat of 1 BTU per pound per degree. That is what we're talking about. That it doesn't take a lot of energy to make water hot or cold. We like that. Energy moves easily in and out of water. It has a latent heat of vaporization of 960 BTUs per pound, which is actually quite favorable. Energy moves in and out easily at comfortable and safe temperatures. It's just the ideal working fluid for energy transfer in any environment where human beings are going to be present and mucking about. Key waterside systems and their functions, or as I like to say, what is this thing and why do I care? So we'll talk about the chilled water plant first. Here's some of the key aspects, and virtually every large site in the modern world will use a chilled water loop for cooling for all of the reasons we discussed in the previous slide. Cheap, easy to move, safe, we like it, all right? So chillers cool water by removing heat. Here's a fundamental thermodynamic concept that I really, really try to hammer home. It is impossible to add cooling. That's a violation of both the first and second laws of thermodynamics. You cannot add cool. You can remove heat. So chillers remove heat from water, and then they have to do something with it. All right, so and we're going to talk a little bit about this later. So they remove heat from the space. How do they remove from the heat from the space? We blow air from the space across a chilled water coil. And because the chilled water coil is less energy dense than the air we're blowing, energy moves from the air into the coil. It makes the water warmer, and then it goes back to the chiller, which removes the heat from that water and sends it out to the cooling tower. This is how most modern buildings achieve their cooling. Now, there's lots of other ways to cool, but this is the one we're going to talk about. And every chilled water system and chilled water systems are by definition Waterside. Has the chilled water loop, and we're going to talk about names and devices on these in a minute, and a condenser water loop. This goes up to the cooling tower, right? The cooling tower is an integral part of the condensing side, and this has a water loop as well. We'll talk more about that in a second. But this is the basic anatomy 101 of a chilled water plant. So, chilled water optimization is a popular product service offered by lots of vendors out there. Managing flow, delta T, and other loop parameters can yield strong efficiency results. How? So glad you asked. Once again, this is the same sort of diagram as we saw in the last one, all right? But there's a chiller. Inside the dotted line here is the chiller, and up here is the condenser side. Half of your chiller is called the condenser. If you've ever seen a big industrial chiller, it looks like 2 cylinders connected by a motor. One of those cylinders is the condenser, sometimes called the condenser bundle. The condenser loop moves water from the condenser bundle to the cooling tower. That's it. It only has one job. And they're not showing it here, but there's a pump in here. An essential aspect of waterside cooling is getting the right flows through both the condenser bundle and the tower. The best way to do this is to make sure your tower requirements match your chiller requirements. That feels obvious. Doesn't that feel like, oh, well, duh, right? The number of times this is not done will infuriate you. The number of times where the mismatch between the cooling tower and the chiller or the condenser loop in the chiller causes problems is too darn high. There can be a benefit to varying the flow through the condenser loop, but it's more common and more successful to simply install a VFD in the tower fans and let the loop flow stay constant. That is a sort of a critical differentiator between the air side aspects and water side aspects. Don't worry, more on that later. The other main water side system we're going to talk about is the hot water loop. That usually almost exclusively involves a boiler. Boilers produce hot water or steam that provides heat for various applications in water side HVAC systems. Keep in mind, a steam loop is a water side loop. We're not going to talk about them because they are out of fashion and they're getting fewer and further between, and they have their own unique fun. But remember, we can't add cooling, we can only add heat. The boiler has one job: it puts heat into water. And inside any hot water loop, especially one with steam, you're probably going to find the heat exchanger playing a role in more than one place. At the very least, every boiler is a heat exchanger or has a heat exchanger as an integral part of it. Boilers and heat exchangers are critical components. All right, they have to work correctly. They have to have correct flows. They have to have correct delta T's, or you get problems. You get underheating, you get overheating. And in the case of boilers, especially steam boilers, you get significant life and safety risks. I like to tell stories. I'm currently doing a lot of work and consulting for a very famous, very popular, very expensive hotel in a very expensive part of the world. And their boilers are a significant life and safety hazard as it sits right now, mostly because they run them at extremely high pressure and haven't maintained them since Ronald Reagan was in office. So that is one of the challenges we're having on that particular waterside system. And before I get too deep into this and start talking about loops and pumping, I should point out the most neglected, the most ignored, the most available energy efficiency optimization you can do on any system, and especially any waterside system, is maintain it properly. And that is so neglected. Maintenance is very much the forgotten stepchild of the industry, where site operators or building owners simply do not put the time and effort to aggressively maintain these integral critical systems. And you end up with buildings that are going to blow up, or hotels that can't make hot water for the guests, or other perhaps less advantageous scenarios. And of course, any waterside system, we're moving water, we're going to have to pump it. We're going to have to move it around. And I, for one, love the AI generation, simply because looking at this picture, it is very clear that this is what artificial intelligence thinks a pumping station looks like. Just to give you some fun notes, look at the bends in those pipes. Absolutely nobody does a soft arc like that. Pipe, 45-degree cutoffs, no check valves, anywhere to be seen. If you're worried about AI taking our jobs, I think we're all pretty safe. Pumps are pipes, valves, pumps, all of that. That's how we move it around. If the pump is the beating heart of the waterside system, the pipes and valves are the arteries. Proper design of pumps and pipes maximizes flow efficiency and reduces energy consumption. And I should point out that in a very large distributed waterside system, the water has weight. It takes energy to move that water. So you want to make sure you're only moving as much as you need, as fast as you need to move it. And I just said this, but yeah, pumps are the heart of all waterside systems. If you don't move the water, you can't use it. The reason we use water to transfer heat is because we can add or remove heat to it in one place, move the water to another place, and then add or remove the heat from the water. It's a way of transporting. It is an energy transfer media. In and of itself, it does none of the heating or cooling. It simply allows us to move the energy around. The energy we want to extract from the building when we want to cool it down, or the energy we want to add to the building when we want to heat it up. So you have to move the water. Some key terms and definition when you're dealing with pumps and pipes and all of those things. Head, sometimes in feet, sometimes in meters, that is simply a fancy word for pressure. It is the height or equivalent pressure you would need. A pump can raise the liquid. It's independent of fluid density, but we'll get into that. So what does that mean? It means that if my pump is rated for 10 GPM at 15 feet of head, GPM being gallons per minute, it means that when that pump is operating correctly, it will lift 10 gallons, 15 feet every minute, period. Now people ask, well, what if I only have to lift it 5 feet? All right, then the head will go down and the flow will go up. What if I try to lift it 15 feet? Well, it's going to get less flow. It now has to lift it more. It has to lift it further. And for years, we've been calling that head. Why do we call that head? I'm not really sure. That's a very, very old term left over from boilers, steam boilers and steam engines. Basically, it's related to horsepower. But it is very, very specific. You say, it's got 50 feet of head at 100 GPM. That means it's going to move 100 GPM 50 feet into the air. GPM, liters per second, or gallons per minute. Obviously, it's simply the physical volume of liquid moved per unit of time. Pump curves. I considered doing a pump curve slide. I'm not going to do that to you people. That is its own fun. It's just basically a manufacturer's chart showing how flow and head vary with the speed. They say impeller speed, shaft speed, whatever. It's basically a chart with a bunch of curvy lines, and you say, okay, if I run the speed at this and I run this much flow, I'll get this much head. Or if I run this much head, I'll get this much flow. If you're not sizing and installing pumps, don't worry about it. The best efficiency point, there's actually about 37 different acronyms for that, but that's the one that gets used the most around the world. It's the point on the curve where your efficiency is highest and your internal losses are lowest. It is very, very important to note that pumps and motors have a sweet spot. They have a place where they just do the best, and you want to keep them there. Net positive suction head, that's the minimum suction head above vapor pressure to prevent cavitation. I put that one in here for the people who've been around the block a few times. All you really need to know about net positive suction head is that if you do it wrong, you blow the pump up. That's it. So you're gonna want to keep that term in mind, but don't worry about it. Variable frequency drive, for those of us who work in the industry but don't actually work specifically with the maintenance or installation of pumps, pipes, and waterside systems. If you work in energy efficiency, the variable frequency drive is probably the term you need to be the most familiar with. They are heavily sold devices. They are heavily oversold devices. It's an electronic motor control that varies pump speed to match system demand, reducing energy use. And that definition is great, except for in the real world, it's more like expensive widget purchased, installed and commissioned incorrectly that doesn't do a darn thing. Both of those definitions apply. It really depends on who put it in. And then series and parallel operations. Series adds heads add at same flow for high resistance systems, parallel flows add. What that means is if you put your pumps next to each other and have them feed the same manifold, they will double their flow. If you put them in line with each other and have one feed the other, you will double their pressure, their head. That's all. That really, it comes into play when you get into specific systems. All right. So, and I warned you about this at the beginning, and I apologize if you're not a math person, but we're going to do a little bit of math right now, or at least I'm going to show you some math. We're not actually going to do the math. Relax. You'd all use ChatGPT to do it anyway. The affinity laws. What are the affinity laws? The affinity laws are a series of mathematical relationships between the speed of a centrifugal pump, its power, and its flow. Those three things are related by the laws of thermodynamics. You cannot break those laws no matter what the vendor tells you. Please don't break the laws of thermodynamics. They're the laws of the universe. If you break them, you break the universe, and we have no spare universes. So keep in mind that no matter what a vendor tells you, these laws are immutable. They cannot be broken, all right? So you cannot, as we discussed previously, if I raise the head, if I raise the pressure, I'm also going to increase the flow, and that's going to increase how much energy it takes. If I reduce the flow, well, then the pressure is going to come down, and I'm going to use less energy. They're all related. It doesn't matter which dial I wiggle. They all move together. And if they move together in a nice linear fashion, that would be awesome. But the universe doesn't like us that much. It's got to make it a little bit weird. It is a dance between flow, speed, and power, and it's a little complicated, but not too complicated. I don't want to scare you. All right. So VFDs, variable frequency drives, take advantage of this relationship to carefully match pump power to pumping needs. All right. If you really want to know, it's basically, if you're any electrical engineers on the call, it's two inverters feeding pointed at each other with a bank of capacitors in between. AC current comes in, converts it to DC current, loads up the capacitors. Capacitors discharge into another inverter at exactly the frequency we need them to, and it comes out as AC at a different frequency, which changes the speed. There's a whole training on pumps if you want to know how any of that works. So here's how they look. Flow, head, and power. Flow, pressure, and power. Remember, power is what you buy. Power is what you're buying from the utility, so that's what gets everyone excited. When I change the pump speed, N if you want to do algebra, or the impeller diameter, don't worry about the diameter. All right, Because assuming in this case, you're not going to change the impeller when you install a VFD, right? Right, of course you would. That'd be idiotic. So flow is going to change linearly with the speed. If I double the speed of the pump, I double the flow. If I take a pump at 100 GPM and I double its speed, I will get 200 GPM. Awesome. The pressure, the head, raises with the square of the speed. So if I double the speed of my pump in the previous example to 200 GPM, my flow goes to 200 GPM, whatever pressure it was at is going to square. So if that was at 10 feet of head, it's now going to take 100 feet of head. 200, my 100 GPM at 10 feet of head has become 200 GPM at 100 feet of head. That's a big jump. And power, as many of you who are reading ahead have already figured out, will vary with the cube. The power jumps up X significantly faster than anything else. And it makes sense. We've doubled the flow. We've squared the pressure. We are clearly going to need a lot more power to do that. That is a law of the universe. There's no freebies, right? There's no perpetual motion, right? So the inverse of that is if I can reduce those speeds. 80% speed is 51% power. So if I can take a pump motor running at 100% speed, 60 hertz if you care, and run it at 80% of that, it's only going to use 51% of the electricity. That gets people very excited. Wait a minute, I can turn it down 20% and save half the juice? Yes, but you're only going to get, let's see, 20% reduction, 0.8 squared. 0.8 times 0.8 is, oh, that's right, you guys can't answer. 0.64. I'm going to reduce the head by 36% when I do that. I've saved 51% of the energy, but I've reduced the pressure by 36%. And I've cut the flow by 20%. So I'm saving a bunch of energy, but keep this in mind. If the system that this is on needs more head than 64%, then you haven't done anything, you've broken it. You're not going to get the correct flow. So yes, you're saving energy, but you're also not doing the job. And that doesn't make anything more efficient. Efficiency is using the correct amount of energy, not just using less. So flow and head adjust dynamically with system demand. Variable for flow or chilled hot water loops. The savings are exponential, so even a little bit of speed reduction at part load can drastically cut the use. That's why we like these things. That's why we sell the heck out of them. But what you really need to keep in mind is don't break the system. What happens with vendors when they sell these things, they assume ludicrously low operating parameters so they can show very, very large savings. Not every system can be turned down a whole heck of a lot before it breaks. Here's the fun little graph so you can kind of see what it looks like. As speed goes up, you can see how the power jumps. Generally speaking, keep in mind, if you can get it down here, save 30%, you're doing great. You're killing it. You're crushing it. All right. Now that you understand how we pump, how we move the water, let's talk about what we move the water through. Primary and secondary loops. Most waterside pumping loops do come in those two varieties, primary and secondary, with a couple variations. They're usually combined into what is called a primary secondary for reasons we are about to discuss. Lots of older sites, though, and I see them all the time, they still have what we call simple primary loops, where there's no secondary. They just pump all the water, and we're going to talk about that. So primary, secondary with variation. This is the modern standard, all right? This is how most waterside systems were designed between the years of 2006 and today. If your building is older than that, you might see some strangeness. If your building is very, very new, you might see some cool strangeness, some interesting strangeness. On this one, it doesn't matter. Here's your heating and cooling source. A lot of ways to move the water around. Some are more energy efficient than others. Some are cheaper to install and maintain. I have the wrong graphic in here. This is not a simple primary loop. This is a, oh, it is. I'm sorry. This is not a simple primary. Sorry. It is a constant flow. This is not simple primary. Sorry. My fault. This is, in fact, a constant flow system. How do we know it's constant flow? If you want to sound smart in the next meeting, that's a three-way valve, okay? So when this coil wants heating or cooling, this valve opens and allows water to pass through the coil. It goes, once it's gone through the coil, it's either given up heat or it's either given its heat or extracted heat, depending whether it's heating or cooling. Doesn't really matter for this example. And then it goes right to the return side. That's a check valve to make sure it doesn't go backwards. All right. So when this one wants energy, this opens up and lets it pass through the coil. So it gets energy. The coil gets energy. When the two-way, this is a three-way valve. More typos, my goodness. The water bypasses the coil. All right. This closed. So no water can travel through here. It stops here. This one opens and it passes through. The pump sees no change in flow or pressure. That's the critical difference with this system over other systems. No matter what the coils are doing, no matter what the position of this three-way valve, this pump sees the exact same pressure. It sees the exact same flow. And we designed them this way for years and years and years because it protects pumps and motors. Before the VFD was common, before we could change those speeds, varying the flow and pressure through a pump was very, very bad for the pump. It was very, very bad for the motor. And so we didn't do it. We designed these systems to make sure no matter what happens, the pump sees the exact same flow. Very, very good for the pump, very good for the motor. That is how it was done. Now we're going to add some variation. How do we know this is a variable flow loop? These are two-way valves. All right, how does that make a difference, Andy? So glad you asked, voice in my head. So right now on the primary side, this primary, which is just a chiller, all it does is pump water through the chiller. Happy little pumps, no variation, everything's happy. And this is very, very common, by the way. We don't see a whole lot of variable primary loops, all right? When this coil wants energy, when this coil right here wants energy, this is a chilled water loop. So when it wants chilled water, this valve opens and the water can flow through the coil and it can absorb energy from the space. The water gets hot and it goes directly to the return side and goes back to the primary loop to get chilled once more. Everybody's happy. When it closes, all of this flow ceases to exist. The pressure drop through this bit of pipe, the pressure drop through that coil, the pressure drop through this valve, the pressure drop through all of this return piping, they cease to exist. Flow stops. Well, if I've reduced the GPM and if I've reduced the pressure drop, then my pump doesn't have to work as hard. So when this coil is not using energy, when the space doesn't need this coil to do anything, I just don't use that coil. And all of this goes away. If this coil was rated for 10 GPM and had 1 foot of pressure drop, well, then this pump no longer needs to produce that 1 foot of head and it no longer needs to produce that 10 GPM. It can stop. No, it can't stop completely because these other two coils might want energy. But now if we have a VFD on that, we can bring that speed down and enjoy those savings. This is how most of our chilled water systems are in modern buildings. We have a simple primary loop and a variable flow secondary loop. All right, these pumps have one job. They pump through the chiller. All right, so who are the real heroes? We talk about the big equipment all the time. We talk about the boilers, the chillers, the cooling towers. It's the control valve and the coils. When I do an energy audit, when I'm walking through a building, I will spend more time looking at control valves than I will the chillers. They are more important to me. First one, there's more of them. In a big building, there could be hundreds of them. But they tell me so much about how a system is and is not using waterside energy. Most modern coils are equipped with some kind of control valve. In ye olden days, in the days of yore, it was not uncommon to simply have no valves and everything and just have everything get water all the time. And you would use either a face and bypass damper, which is an air side thing, so I'm not going to cover that, to control how much energy the space saw. Or you use hot deck, cold deck was the other way. That's an air side thing, not part of this conversation. But pretty much everything made after 1990, they used control valves. The type of valve selected determines whether the system is constant or variable flow. That should be familiar to you at this point. We just talked about that. When we use two-way valves, we create variation. When we use three-way valves, we maintain flow and pressure. There is no variation. And for the record, the V in VFD stands for variable. So if you don't have variation, why did you have a VFD? I've asked that of many VFD salespeople over the years. Hey, you sold them this VFD. It's great. Yeah. They have no variation of system. It's all three-way valves. Where are you getting your savings? And then you listen for one of two things happens. You get crickets, you get that shocked deer in the headlights look, or you get a lie. That's the nature of it. VFDs, especially through the early 2000s, were heavily oversold onto older buildings that couldn't afford big retrofits. And the salesmen would come through with their big utility incentives and say, hey, the utility will pay for you to put these devices, these magical widgets on your motors, and you're going to save a lot of energy thanks to the affinity loss. And they would have beautiful charts and lots of math and it looked very, very good. But they would not replace the three-way valves with two-way valves. And so the system would experience no variation. I bring that up because that is still extremely pervasive. For the record, after 1 billion square feet of audits, I can tell you that 50% of the VFDs in the field either do not modulate or undermodulate. They have not been properly set up for variation. So keep that in mind. So let's talk about it a little bit tighter, a little bit easier to see in this graphic. So the two-way valve, as you see here, when the valve closes, the water stops dead. That is so important. The flow ceases. It cannot and will not flow. It will not move water. When this happens, the volume of water associated with this coil no longer needs to be pumped. That's it. Not to mention all the pressure drop and all that. It goes away. With a three-way valve, as you can see, it bypasses. Water bypasses the coil when it's not needed. Flow and pressure remain the same, whether the coil is doing a darn thing. And by the way, if you don't understand any of these symbols, and if a lot of the words I'm using aren't hitting you in a way that resonates or that you truly understand, don't worry about it. All you need to know is on a two-way valve, you have variable flow by definition. On a three-way valve, you do not have variable flow. They're pretty easy to spot in the field. We'll show some pictures. But when that VFD salesman comes through, or that energy ESCO comes through, and they are recommending VFDs on everything, wouldn't hurt for you to check and make sure that what they're recommending actually experiences variation. So in a chilled water loop, back to primary and secondary, the primary loop has one purpose: keeps flows for the evaporator bundle within the manufacturer's specifications. Why is that important? Most chillers made before 2010, 2015 did not tolerate a lot of variation in their primary flow. They simply did not have the capability. And what would happen is if not enough water flows through the evaporator bundle, which is the big black bundle here, by the way, this is the evaporator bundle. Actually, the condenser's behind it, it's hard to see. They would over condense. The water would get too cold and it might freeze. So a couple things happen in a chiller, just so you guys can explain to your people when you talk about simple primary flow through the chiller. If the evaporator water in a chiller gets too cold, it might start to over condense, which means it might start making too much cold. There's not enough difference between the temperature and the refrigerant temperature for energy to transfer efficiently. And that means you'll get liquid refrigerant back through your compressor. That is called flooding, occasionally called slugging, but it's technically called flooding. And there's very little in this universe that will destroy a compressor faster than liquid. You cannot compress liquid. That's one of the things that makes a liquid a liquid. It's one of the defining features of liquidity, is that it cannot be compressed. It is an incompressible medium. And if your chilled or evaporator bundle gets too cold because you don't have enough water in it to extract heat, you run the risk of returning liquid refrigerant to the compressor. And that will destroy it. Nothing will destroy it faster than that. Modern chillers are very, very smart. When they detect this, they shut themselves off. Modern EMSs are very good at sending an alarm when this happens. Modern site operators, on the other hand, do not do a great job of acknowledging those alarms. And if they ignore a compressor shutdown due to flooding or to over-condensing conditions, the modern chillers are smart enough to simply wait for that refrigerant to re-evaporate and they restart themselves. So the problem gets ignored and it very, very quickly destroys the chiller. So don't do it. Make sure that your primary loop flows are correct for your model of chiller. Now, if you bought a very, very modern chiller, the really, really nice ones nowadays, they actually tolerate quite a bit of variation through the evaporator bundle, and then you can do a variable flow primary loop. That's less common, but if you're in the modern, if that's the system you have, awesome, because they're very energy efficient. But the rule of thumb is you should be moving exactly as much water through your chiller as the manufacturer tells you to, and that's the job of the primary loop. The secondary loop is where we have all our coils on. And I'm showing air handlers here. It doesn't matter where the coils are. They can be a fan coil unit. They can be in a process. You could be cooling an injection molding machine. It doesn't matter. The secondary loop is what has the loads on it, the coils. Coils are most important part of any chilled or hot water system is the coil, because that is where the energy interacts with the space. All right. If you set it up correctly, you can vary the flow through this loop. And how do we set it up correctly? I'm going to assume you're all going to say it along with me, and that's we're going to introduce variation. We're going to put two-way valves on those coils so they don't immediately bypass to the return side. Now you can vary the speed of these pumps to your heart's content and save huge amounts of energy. It can be saved if your secondary loop has been equipped for variable flow. Put your two-way valves on. I should say, put your two-way valves on and then commission them. What do I mean by commission? For those of you who don't know, that means somebody who knows what they're doing goes and checks and makes sure they're opening when they're supposed to open, closing when they're supposed to close, and that the correct amount of flow is going through them given their position. That is a process. There are commissioning agents. Your HVAC contractor, your installer should be doing this, and for the most part, they will with varying degrees of competence and care. That is between you and your contractor. Properly commissioned variable flow loops where the valves talk to the EMS or they talk to the VFD and they do it correctly, save enormous amounts of energy. Improperly commissioned loops save very little energy and occasionally break stuff. All right, but as the cooling load varies in this case, this system allows you to pump less chilled water through the site. That means pumping less energy. And hot water loops follow all of the exact same rules. I wasn't joking. The affinity laws are laws of the universe. There's no condenser side on the hot water loop, which is nice. And they benefit from variable flow in the exact same way. And as you can see, we have it here. We have two-way valve, two-way valve, two-way. Why is there a three-way valve at the end of this one? You put a three-way valve at the very, very end up to the last node in the system, simply to make sure that there's somewhere to bypass excess flow. That's all. It's a safety feature. In many cases, it's not necessary. You can even do a static pressure bypass here just to be safe, but that is common design. It's good design. So if you're walking through your building and you see a three-way valve on a coil, and you think, oh, that should be a two-way valve, just make sure that wasn't meant to be there. Should be only one though on each loop. A note from my father, one of the pioneers of the energy efficiency industry, is if you see something in your building that looks like a mistake, don't assume the person who did it was an idiot. Assume that person knows something you don't. In my experience, 7 times out of 10, the person is an idiot. But the 3 times out of 10, they weren't an idiot. It saved my keister to not immediately assume they were. You don't want to be the guy who breaks the building. If you're enjoying this training and you are an energy auditor, energy consultant, certified energy manager, if you have an energy efficiency role, a building retrofit role, it is very, very important, in my opinion, for you to understand the concept of just because a thing looks wrong doesn't mean it's wrong. Rules of thumb are exactly that, the rules of thumb. They're not rules of the universe. So don't go making grand changes without really understanding the system, because you're going to be the guy who breaks the building, and then you will have absolutely no friends. All right. But in this one, you can see it looks exactly like our chilled water system, right? We have primary pumps on this side because boilers really enjoy steady flow, just like chillers. Very few boilers, even modern ones, like to have variance in their flow because the delta T's in a boiler are much, much higher. I have a slide on this coming up we'll talk about, but delta T simply means a difference in temperature. So the return water temperature is just, for example, on a chilled water system, you might be sending the water out at 44 degrees and it might be coming back at 54 degrees. That's a 10-degree delta T. When the water comes back from your hot water system, you probably sent it out at 180. It might be coming back at 160 if you're under load. However, the refractory of that boiler, the place where the fire happens, is 2,000 degrees. So instead of a 10-degree delta T at the refractory, you have a 1,840-degree delta T. All right, boilers are built tough, they can handle that. But if you start sending the wrong amount of water back, or water that's too cold coming back, you will crack that refractory. And now you're buying new boilers. So boilers are a little more sensitive to the primary flow issues than chillers are. That being said, as boilers get more advanced, that's less and less of an issue. So pipes and valves. I actually don't have a lot to talk about on pipes themselves. We'll mention there, but these are different types of valves. Your building has hundreds of these unto thousands of these. They all do the same thing, but they all have a different job, and they may do them in slightly different ways. Water has to move through something or everyone's going to get wet. That's the reality. Pipes have been in use since the Bronze Age. This is not new technology. There's existing archaeological examples of water pipes, clay water pipes, being used in civilizations going back to the Bronze Age. We know how to move waters, is all I'm saying. Valves allow us to change the flow and direction of the water we are pumping, often both. Valves will do do one or more of the following tasks. One, they're going to prevent flow from going the wrong direction. We call that a check valve. We want the water to move in one loop. It goes around in a circle. You do not want water moving backwards. That is bad. It's going to prevent pressures from getting too high. That's a relief valve, sometimes called a pressure relief valve or a safety valve. Your boiler will have one by law. And when it detects things are getting under too much pressure, this little spring you see right here, I hope you all can see my mouse. This little spring you see on the one called relief valve here is set to a given pressure. When the pressure gets strong enough to compress that spring, it's going to let some of the water or gas or whatever out. That way you don't have an explosion. A steam leak or a water leak is a pain in the neck. An explosion, that's a catastrophe. Some of the most energetic explosions in the world, by the way, are domestic hot water heater explosions. Mythbusters did a great episode on when they got one to blow by disabling the safety valve. They launched that residential size electric hot water heater about 300 feet into the air. They are devastating. There's far more energy in water than there is in air. So when water explodes, it is not insignificant. All right. So yes, your relief valves are important. They can reduce flow rate or control flow rate. So you've got your pressure reducing valves, your throttling valve, sometimes called a balancing valve. All these do, and they can be of any of the kinds you see here, is they restrict the flow of water so the outlet side of that valve is at the correct pressure and the correct flow for whatever your system needs. And in the days before VFDs, this is how you balanced the building. It's how you balanced all these flows to make sure you didn't blow out coils or make sure you had the right amount of flow through a coil, is you would use throttling valves or balancing valves to get all your flows exactly where you want them. In a large building, you might have miles of pipe with twists and turns and bends. At some point, no matter how well you design it, you're going to have to tweak the flows. And that's what your balancing valves are for. They can direct the water through a coil, a control valve. We've talked about those. From an energy standpoint, those are probably the most important. When a space needs energy, when it needs chilled water, or it needs hot water, or it needs condenser water, or it needs heat pump water, whatever it needs, these are the valves that open and close and let that space have it. Very, very important, obviously, for occupant comfort and maintaining the desired temperatures in the building. They can combine two flows, a blending valve. Most of you who, if you've ever used a faucet, you've used a blending valve. That's purely to simply get water at the correct temperature. You blend hot with cold. Or they can isolate part of the system so it can be worked on. That's called an isolation valve. If I need to work on a pump, and I don't want to shut the whole building down, each side of my pump is going to have an isolation valve. I'm going to turn those valves so I can work on that pump without emptying all of the water out of the system. Every node in a waterside system is supposed to have isolation valves, so it can be isolated from the system to be worked on. In most places, that's code. Most places, that's a law. It's always good design. That being said, if you have the home improvement network, the number of times you see in residential, it's mostly in residential, where they simply didn't install the isolation valves, and now you have to drain the whole system to work on anything. It's a thing that happens. It's a way of saving money to simply not put them in. Of these valves, just some quick tips for when you're in the field. Doesn't matter if it's a gate valve, a diaphragm valve, or a globe valve, or a piston valve. Wherever you see these big wheels, that particular style of closure is called an outside stem and yoke, OSY. Don't worry about memorizing it. Here is the deep magic. Here is the lore. All of these valves are completely in the closed position. How can I tell? Because if they were open, there'd be a big piece of threaded rod sticking out of the top. The more, see this rod right here? God, I hope you guys can see my mouse. As I open this valve, this rod will extract until it's way out the top. You can tell whether these valves have been throttled or whether they're open or closed by the position of the stem. This is the yoke. This is the stem. The stem is inside the yoke. On this one, you can see the yoke is easy to see. Yoke is easy to see. This yoke is it's still technically a yoke, even though it doesn't follow the yoke paradigm. That way, if you're ever walking through and you want to know why isn't the water flowing, and you look and you can see that the stem of the valve is way out here, you know it's because the valve's closed. That's a little trick. On any valve with a handle like this is a ball valve. This is a butterfly valve. Sometimes you hear this called a ball cock, but for some reason people don't want to call it that anymore. It's because it's cocked. When you cock it, that is what tells you the position. If it is installed correctly, and actually, it's almost impossible to do it wrong, but I've seen it done. The handle will indicate the position of the blade of the valve. So this valve is in the open position. If there's water flowing through, this handle is in line with the water, which means the blade of the valve is in line with the water. This valve is open. If I want to close this valve, I turn this 90 degrees, and now the handle of the valve will be 90 degrees to the flow of the water. That's how I can visually tell it's closed. Same thing with this particular butterfly valve. All right. I have seen these installed incorrectly. I have seen these when they're damaged, so this is not the case. So do not take it as gospel. But under normal conditions, if it is otherwise correctly configured and installed correctly and not broken, you can tell the position of these valves by the position of the handle. It should always be in line with flow if you want it open, or 90 degrees to flow if you want it closed. And then, of course, here's a control valve, a nice big one. This is automatic. This is either pneumatic or electric. It doesn't really matter which, although pneumatics is going the way of the dodo. And some piece of equipment, some sensor somewhere would give a signal to either open or close this. But these are the valves you're most likely to see in the system. But there's one special kind of valve that I love more than most. The most interesting valve of them all, the triple duty valve. These will be mounted to the outlet side of most pumps in a modern building. It's just good design, and we've been doing it since early 2000s. It is one valve that does three very important jobs. It is a check valve. Water will only go one direction through this valve. It is a balancing valve in that it can be adjusted to maintain proper flow, proper pressure. And it's an isolation valve. You can just close that thing off and work on it while you service the pump. These are extremely popular because instead of buying three valves, you buy one. It makes them very, very popular, and they do a fantastic job. And this is an Armstrong one. I picked them because they had a good diagram. They don't always look exactly like this, but they often look a lot like this. This is the important part to you as an energy person, as an energy auditor, someone in the field trying to determine what your waterside system is and is not doing. It tells you what position the loop has been balanced to. I hope you can see it in here. These little graduations are these little lines. Each one represents 10% open. So the more of those I see, the more open it is. The fewer of those I see, the more closed it is. And this is a permanent fixture. This does not move. So that means when someone installed this valve and they balanced the entire system, they cranked it to that position because that is the position they wanted it at. Is that the best position for it? That is for you, the energy professional, to determine. It is very common to find this valve throttled even when installed in a variable flow loop. And that just grinds my gears. If you have a VFD installed, you're usually wasting energy by throttling it. When I train new energy auditors, it's one of the first things I tell them to look for. Variable frequency drives will adjust speed, flow, and pressure. We talked about this, we have a whole slide on it. Don't make me go back to the slide. Whatever flow, pressure that your loop needs, the VFD can find it on its own. That's why we like them. There is no need to balance it further most of the time. Generally speaking, the best practice is to open this all the way and let the VFD find the correct pressure. Your commissioning agent, whoever installs your VFD, should be doing this. Now, in some situations, weird loops, all that, you might need to throttle a little, you might need to balance this a little bit just because your building is a special, unique snowflake, and that's fine. But 90% of the time, this should go all the way open because this is artificial restriction. This is artificial pressure drop. It's going to force the VFD to run faster when it doesn't have to. The number of variable flow loops with VFDs and throttle triple duty valves out there is significant. It is the easiest ECM in the world to get, costs very little to do. The only cost associated with this is having a professional there to make sure that you can get away with it, to make sure that it's okay to do it. 90% of the time it is, 10% of the time your building has some sort of special need that needs to be addressed. But that being said, it is extremely common to find this still throttled. How does that happen? Great question, voice in my head. It happens because electricians install VFDs and plumbers balance loops. Whoever's selling you the VFD is probably just gonna have an electrician install it, do the factory startup and walk away. Pay the extra money to do it right. Common deficiencies in ECMs, trying to go fast, I do want to cover the material. The short version is this: proper sizing ensures everything is met correctly. Proper design and proper component selection. I'm not going to read these because I want to go a little faster. Most common issue, we've harped on it pretty heavily, no variation. Why is my VFD not modulating? Your triple duty or balancing valve is throttled too much. The balancing valve in the system of the VFD can be opened all the way most of the time. The VFD should find the correct flow on its own. Recommission your VFD and rebalance the flows. Shouldn't be long dollars at all. Somebody put the VFD in manual and left it there. There are many reasons this happened. Most of them are silly. Some aren't, but most of them are. Check on why the change was made. Correct whatever condition made it necessary. Put the darn thing back in auto. Get your savings. A VFD that's not in auto does nothing. It is an expensive widget. It does no good. Your control valves have all failed. This one happens. We talked about maintenance, or at least enough of them have failed to make modulation possible. If control valves fail, system differential pressure is going to deteriorate and force that VFD to run either at minimum or maximum speed, depending on the specific type of failure. Valves can fail open, they can fail closed. Just survey and repair your valves, something you should have been doing all along. Shame on you. Or the one I love the most, it's just not a variable flow system. Do you have three-way valves? If you have three-way valves, it's not going to vary. You can't expect it to vary. It was never meant to have variation in its flow. The good news is replacing them with two-way valves and recommissioning is rarely long dollars. Outside air reset, common ECM applied to waterside systems. Outside air, this is when supply temperature is raised or lowered based on how hot or cold it is outside. In chilled water system, the benefits of this are actually pretty easy to understand. Warmer water means less chiller lift, period. So the warmer I can send my chiller water, the less lift my chiller has to do, the less work my chiller has to do. With boilers, it gets murky. This is very much a pet peeve of mine. Unless you have a condensing boiler, your boiler efficiency does not change with the supply temperature. Your chiller efficiency does. Different machine doing a different job. A boiler rated for 85% is going to make hot water 85% no matter how much you need or what temperature you make the water. Changing the supply temperature does not change the load. If you need 100,000 BTUs per hour to hold that set point, then you're going to deliver 100,000 BTUs and you're going to buy 100,000 BTUs. That's the reality. You can deliver that heat with water at any temperature you want, but you won't get to change how much fuel you'll need to do it. 100,000 BTU at 180-degree water is exactly the same as 100,000 BTUs at 150 degrees. A pound of feathers weighs the same as a pound of lead. Right? First law of thermodynamics, energy can neither be created nor destroyed. So why do we keep doing and selling this on boiler systems? It can reduce parasitic losses. Pipes and valves filled with 180-degree water lose heat faster than those that are filled with 150-degree water. You send cooler water, you get less pipe and valve losses. The savings exist, but they are negligible. That is a whole other training, but the amount saved by people, claimed by people selling this particular ECM, and the amounts you're actually going to save are very, very different most of the time. And of course, worse, sending cooler water means it takes longer to satisfy the space. Your control valves stay open longer, so your pumps work harder. Outside air reset is not a particularly compelling ECM on hot water systems, no matter what the vendor tells you. And if you are that vendor, or if you have a vendor telling you that, please send them to me. This is one of my favorite arguments to have. The math is on my side, and several national laboratories agree with me. So bring it on. Delta T's out of spec, very, very common in waterside systems. Chilled water and hot water plants have ranges of temperatures where they're most efficient. Keep them there. All right, I'm not going to read the whole thing. How do I maintain it? Step one is to know and understand your manufacturer's recommended operating parameters. Read your manuals. Bring in someone who knows what they're doing. One or the other. Either you're going to do it or you're going to pay someone to do it. But if you don't do it, it's going to cost you money. Monitor supply and return temperatures via your EMS. If you don't have one, you can do it manually. In the old days, that's exactly what they did. A person would go around several times a day with a clipboard and keep track. That's how they prevented steam buildings from exploding back in the day. It still works. The difference between the two temperatures, your delta T, tells you how much energy is being used. A big delta T means lots of energy is moving. Small delta T means less energy is moving. The goal is to put as little energy as possible into the system. Too little means you won't transfer quickly enough. It's a dance. Nowadays, we use computers to optimize it, and it works great. Then adjust your set points to keep differential temperature in optimal ranges. If you're good, you can do this yourself. Once again, if you've got the time, energy, and expertise to sit down and do this manually, do it. It won't cost you anything. Well-commissioned control system is going to automate it, though. That's what you want to do. You want chilled water to go out as warm as possible and hot water to go out as cool as possible. This is a rule of thumb, but it's pretty universal. In all cases, maintain the right DT for your system. We're trying to send supply water at the least loaded temperature that also keeps return water within the optimal range and doesn't blow our equipment up. All right, we're at time. Here's the last slide on just the core principles of chilled water optimization. Read them on their own. It's a dance. It's a dance that operators used to have to do manually. Now there are quite a few systems, products, and services that will do it for you. I cannot recommend them enough on a chilled water system. It's a lot to maintain. I'm going to stop. I got through 90% of what I wanted to, so I'm pretty happy with that.
That's
I'll
good.
open the floor for questions.
Okay, here's one.
Thank you.
Regarding boiler temperature reset. If we're going to reset the boiler temperature, considering the flow is constant, I think that will result in gas savings. What are your thoughts on that? Well, I think you already told us that, right?
Yeah, generally speaking, there is a non-zero savings potential. It is minimal, because you didn't change the load. So if the system needs 100,000 BTUs, you're going to buy 100,000 BTUs plus whatever is lost parasitically. And then changing the delta T reduces those parasitic losses, but going from 180 to 140 reduces the parasitic losses. If you want to do Fourier, how do you guys feel about multivariable calculus? If you do it, it comes out to a very, very slight change in rate of energy transfer. And then, is that energy truly wasted? In most buildings, parasitic losses from pipe, valve, and the boiler do not actually become losses until they leave the building. So if the boiler is underneath conditioned space, all the heat, you go in that hot boiler room, oh, it's wasting energy. If that heat doesn't get outside and stays in the building, it's not necessarily wasted. The math gets
because you're actually heating the building through the walls now.
poorly, but it is so the actual wasted gas is very negligible. It's not there, but it's negligible.
Okay, when you have pumps piped in parallel with VFDs, but only one pump is needed. Yeah. I like this. Wouldn't it be better to run two pumps at half the speed to save energy? Great question. Thank you for asking.
Absolutely. Now, I shouldn't say absolutely. Keep in mind, so, is it better to run one pump at full speed or two pumps at half speed? Yeah,
I've been asking a lot of people this question. Okay,
mathematically, you'd think, all right, well, if half speed is 12% energy, keep in mind it's about how much water you're moving. So
right.
Because if you run them both down, because they are parallel, they're manifolded. All right, so you are increasing flow by bringing another one online, but you have not changed the pressure. So what happens is you tend to have to run them both higher to maintain the pressure.
Right. So the flow, because by reducing both pumps to half speed, you're reducing the flow to half speed, but
you're reducing the pressure to something tiny, 12.5%,
a lot more than
12.5%, right? So at some point, you're going to have to run one of the pumps hot enough to make the pressure.
Right.
So at that point, now there is math you can do to optimize. There's logic where you can figure out exactly the correct point to bring the second pump online. There's an inflection point in every system that is dictated by the actual flow characteristics of that system, where it does become better to turn the second one on and run them both lower. Where exactly that inflection point is incredibly variable. You need a computer to do that. You need it. But yes, modern if you ASHRAE guideline 34.1 covers it if you want to see the actual sequence.
So then I guess what you're saying is you can run two pumps. They won't be at 50%. They might be at 65%. Something like that, or still be
load
running,
is load.
but still,
if I have to move 100 GPM at 100 PSI or 100 feet ahead, I'm going to use the energy it takes to do that, whether I use one pump or two. Now there is an inflection point based on, but it's not as simple because it's like, well, if I run 2 pumps at half speed, oh well, there I get my GPM, but yes, but you're both are now at 12.5% pressure. You won't move the water.
That's right. Okay. Well, it's not 12.5 because it's a square. It's not a cube. So
A square,
right.
25%. Yeah.
Okay. All right.
Yeah,
so here's one. Go ahead. All right. Next one. Can two-way valves close a percentage, or are they only open or close?
They can close a percentage, and the best ones do.
Okay.
Now, the actual energy savings between all the way open and throttled is a non-zero number. It's not huge. So if you don't want to go down that road, you're still going to get most of your savings by going all the way open, all the way closed. But what you get is a valve that's not constantly opening and closing. Your actuator lives longer. Your building can balance itself a little smarter. And there is a tiny, tiny increase in pumping savings doing it that way. Not enough to break the bank over if you're considering one system over the other. They both work great. Yes, the modulating control valve is the superior choice, but not by some giant.
Of course.
You know what I'm saying? Yeah.
Yes. In a constant flow system with three-way valves, is there clearly some change in head based on whether there is flow through the coil or whether there's on whether there's flow through the coil? No. Do you consider the change in pressure for this configuration negligible? Go ahead.
If it's properly balanced, the answer is no. It should be the exact same. If they designed it and built it correctly, the flow should not change. The flow pressure, all of that should stay the same when the valves. There's a whole series of balancing valves and check valves that have no other purpose. I have been in buildings in the old days where they will put extra bends in the return pipe to maintain the correct flow coming out of a coil. They'll introduce artificial restriction. In where it's not been done correctly, yes, there can be a noticeable difference, and that difference is bad for the pump and motor. It's rarely, if it was really bad, something would break. So the thought of, well, I'm going to use a VFD to fix that problem, technically the answer is yes, you're the best kind of correct, technically correct. Under those conditions, if your system is so badly balanced that you are seeing, and they call it a riding the curve, when a motor or a pump is instead of modulating to meet the load, it just rides the curve, it's very bad for the motor. It's very bad for the pump. Don't do it.
Okay, here's a question. This is one I had about 20 years ago, and I was just learning this stuff, but I think maybe someone else thinks like me. Can you go back to your picture showing the two-way valves in the secondary loop? Can you go back to that slide? So in this slide, it's showing, you have three different, yeah.
Well, these are three ways.
Not that
this
one. That one. So you're showing, okay, three ways, right. So you're showing three of them, and then you have this arrow. So the question I always had when I was just learning is, okay, well, what happens at the end of this arrow? I guess it assumes there's more of these, but let's say there's only 3 fan coil units on this circuit. Okay, just 3.
Oh.
Are these 2 pipes connected, the going out and
absolutely.
returning? Are they connected?
Yeah.
Or do they stop?
Imagine this turns 90 degrees south and connects right here.
Okay, now what if it's two-way? If it's two-way, go to the next slide.
Same thing.
Okay.
See, this one shows the whole loop.
This doesn't show it.
They're
not.
The supply side, the insert, and the return side are connected by the last node in the system.
Okay, so if you close all of these valves, let's say that there's no need for cooling, which means your secondary pump can really turn off. It won't turn off because you said you have, it's really a bypass, a line that's going, that you have the supply and return are connected and not going through a coil. And I think that that's not true. I think that this ends at a coil and that they're not.
Yes, that's what you're looking at right here.
Yes. Yes, exactly.
That's why there's a three-way on the last node in the system.
That's right. So if all of these closed, this pump
this one would go to bypass.
That's right.
Yeah, it would. Yeah, theoretically, you could close it if you legitimately had zero load, you could turn the pump off. Absolutely.
That's right. And can you go that the other this doesn't have a bypass. Do you have a primary secondary with a bypass?
Uh,
I don't think there is one, is there?
Depends on the kind of bypass. Any three-way valve is a bypass by definition.
Okay. So can you explain the whole concept of a bypass on a primary, secondary? Because, you know, if you close all the valves, well, first off, you close all the valves to all the fan coil units or air handlers. Okay, so your secondary pump can slow down, maybe even stop, but you still need, the chill water is still going to go through the primary loop. And here, I don't really see.
Here we go.
Let's
look at this one.
That's your bypass. There's your bypass.
Yes.
Right. So these are still going to continue in the primary loop. The water's still going to continue to circle through, and it's not going to.
Most of the time, that is exactly what they did. You keep it moving. Absolutely.
That's right. And the water's going to not choose to go through all, you know, these closed valves. It can't go because it just stopped. There's nowhere for the water to go. So it just continues through the bypass.
So this loop continued pumps in a circle, and the chillers are going to stop chilling too, because this water is going to stay 44 degrees. That's going to tell the chiller. Right. And this 44-degree water is just going to stay in the circle to whenever you need it. A valve opens up, the pump kicks on, it's going to extract exactly as much 44-degree water as it needs, because this pump's going to go to the correct speed. If only one coil opens, it's going to pump just enough for that.
That's right. Okay.
Yeah, that's
and
what
one last thing.
Yep.
If you have a low chiller delta T, one thing I read was a good thing to do is to slow down the variable, the secondary pump.
Yes.
That it's running too fast.
Dwell time. That's the concept of dwell time. So if your chilled water is coming back too cold, there's not enough load, and you don't want it, and your chiller doesn't like that. Your chiller has a special delta T it likes. You slow down the pumping, and so the water will spend more time in the coil. They call that dwell time. And so more energy will be extracted from the space and put in. So your return water should come back slightly warmer with a slightly more advantageous delta T.
That's right, but only slightly. So if you have a delta T of 2 or 1, which I've seen a lot of buildings with that, this isn't going to do it. You're not thinking we can get back to 10.
You see a lot of buildings with a chilled water delta T of 2 or 1. You got to call me more often, John.
I do.
No.
I do. And so my question is,
close the valves.
Yeah. So you don't think just slowing down the pump it's not going to bring it back?
Chilled water delta T is 1 degree. You don't have any load.
No, it should.
Yeah, I know that. Pump that water around again, John. Pump it around again. If you send it out 44, it comes back 45. Pump it around again. Keep pumping it around until it comes back warm enough. Then send it through the primary.
Yeah. Then turn on the chillers. I know it's crazy.
And that's a setting. That's a setting. You just set that. It's going to if your controls are commissioned, you're going to keep pumping that water in a circle until it hits the correct delta T number. Then the bypass is going to open and send it back to the primary. That's just controls, man. That is chiller optimization 101. Good. Don't be sending 1 degree water back to the primary. Everyone on the call, don't be sending 1 degree delta water back to your chiller. It doesn't want it.
Geez.
It doesn't want it.
Dude, you don't know how much of this I see. Okay. That's all I got. I don't think I have any more. Let me just check one last time. I think we went through all the questions. I'm surprised. I thought there'd be more than that. They really liked it.
Oh, good.
They did. Here we go on something on dwell time. For dwell time, I've heard of Vaillencourt energy valves that are controlled based on the DT across the coil to help increase the heat transfer to the coil. Is that a good solution versus changing the pump speed?
It is a good solution if you have the money for Vaillencourt energy valves and you don't want to mess around with your chiller loop. You can accomplish, it sounds like the questioner already figured out, you can accomplish the exact same thing by controlling your pumps, and that is correct. That is absolutely correct. You can also keep in mind a Vaillencourt energy valve is a modulating two-way control valve, and it does an excellent job. It's a very fine product. If any Vaillencourt people on the call, I'm not knocking it, but it does a job. It makes a job that used to be very difficult, very easy. But now with modern chilled water optimization controls, sequences, vendors, and all of that, you don't need the Vaillencourt valve. Now, if you can afford it, they do a great job. Absolutely, no question. It is probably the most technologically sophisticated control valve in the world. it basically removes some of the work from your EMS and makes it internal to the valve itself. They have to be maintained carefully, and you have to know what you're doing with them, or you starve coils. And they mostly take advantage of the flywheel effect.
There's cases where you have administration that's not interested in investing money in chiller optimization and all that stuff. And you just want a quick fix. I just want to go on site, make a quick recommendation, and try to resolve this chiller delta T. That's not going to cost some money. We just want to change a few settings. That's what I'm looking for. What would you recommend for that?
Yeah, if you've got no money and you want to optimize your chilled water plant, step one, and by the way, this applies to your boiler water plant too, pick up the manuals and read them for real. Really read them. Then do everything you can to keep your delta T's and your flows through that chiller exactly where the manufacturer tells you to. Sounds easy, can be tricky.
Yeah, sounds easy. Of course
and if your entire building is otherwise in good shape and you have a good EMS and you know what you're doing, it actually is kind of easy. Now, how many buildings have I been to where they had a good EMS, the building was in good repair, and the people had the knowledge and skills to do it? 2 out of 3 ain't bad. Yeah. You know,
3? I know 1 out of 5.
Yeah. So the point is in the days before we had all these wonderful technology, people maintained optimal chilled water plants manually. It's just work.
All right. So you're okay. Good. All right, you guys. Do you have any parting words? Any last words?
From me?
Yeah.
I guess if you really, really want to run your site really efficiently, especially any of your water site systems or anything, the best thing you can do is educate yourself. The vendors will try to help you, but they're going to try to help you in a way that benefits them. They don't always tell the truth, and they don't always do very good math. Your site operators are already doing the best they can in most cases, and if they're not doing the best they can, get new site operators. Educate yourself, not just because we do this, but just I audit 100 million square feet a year, and I spend a lot of time talking with people who really just don't know what's going on in the building. You want to save energy, learn what's going on in your building, learn to drive your building. That's all I can really say. Probably the best thing you can do.
Okay, guys, everyone, thank you. Andrew, thanks so much for coming.
My pleasure.
I want to have you back. Let's try to do one next year. Maybe we can do Airside.
Yeah.
Thanks, everyone.
All right. Thank you, everybody.
We'll find. All right. Take care, everyone.